Hi there, everyone. I want to record a short video here going over some of the quizzes. You see the quizzes feedback is here under this review of Chem 131 tab. So let me go through this. First of all, the September 11th quiz, I had asked you to basically the same question that I asked you the first class meeting we had was to look at the periodic table, look at a particular element, and tell me everything you could figure out from it. So before I graded these things, I sat down and I thought, okay, what would be a reasonable sort of thing for someone to get from the periodic table? And I came up with this list here. It's not perfect probably, but I think it's pretty good of what you should get from the periodic table. And again, I emphasize that I wasn't asking you to go to another source and find out other things about the element. I was asking you, what can you get from the periodic table? Because I figure anytime you're in a class in the future, you'll at least have a periodic table available to you. And there's a lot of information there that you need to know how to unpack. So anyway, so I came up with this list, pointed them out like that. The first few ones were a little more important, I thought, and then less points down the way. And then 10 points of the 30 points in the quiz were given for on-time submission. If you didn't submit it on time, I gave you 6 of those 10 points. This is a, or. That's out of 10 of the points, and that's 20 of the points, and the quiz itself is out of 30. I copied this list over into your comments and then would put the grade in front of your thing like I would, if you got the name and symbol right, I would say 202 points, for example, in front of that so you can tell where you got and where you lost your points. So my ID number at JCSU is 3052. You can tell I'm an old timer because I have a 4-digit ID number. 52 is element Te, which is tellurium. It has, if you look on the periodic table, here, let me get my periodic table here and show you this. You'd see something like this, 52 Te 127.6, and that is in group 14, 16. Or 6 in the Roman numeral way of numbering it. That's the same group as oxygen, right? So I was able to figure out that this number is the atomic number. It's the number of protons. It also gives me the number of electrons if it's neutral. The average atomic mass is this number at the bottom, the 127.6. That number, if I put the units of AMUs on it, is the average atomic mass. If I write it, if I put grams per mole on it, or write it in these two conversion factors here, it's the gram to mole conversion factor, which is what we use it more for than anything else. If we count through the electron configuration, it's 5s2 4010. That should be a superscript, not a normal number, 5p4, with a krypton core, which is acceptable. And if I do the orbital diagram, which I did with Word and typing here, so it can be done, these arrows are under the symbol. They've got, the up arrow and the up arrow with the line the other way, and the down arrow and the down arrow as the line the other way. All of those are options in the symbol, insert symbol in Word. So anyway, so what happens here, what's important to note is that in the 5p orbital, you wind up with 2 unpaired electrons. That is, what would not be the correct one is where you draw it like this, where you put all those electrons in the same orbitals and pair them. That's not allowed. That violates Hund's rule. Now, in terms of the isotopes, it's, unless you're looking at a radioactive element where you have a average atomic mass is a whole number and it's in a bracket, that tells you what the most long-lived isotope is of an element that only has radioactive isotopes. Looking at 127.6, It's probably reasonable to speculate that maybe there's an isotope that's 127 and 128, but I don't really know that. There might be ones that are lower and higher. For example, if you looked at bromine is 79.9. You might assume that it's mostly 80, and I think it's actually half 79 and half 81 is what the bromine one is. Anyway, but if a reasonable speculation, though, would be something like this, that there might be two isotopes of mass number 127, 128. If 170, 127.6, there would be a slight excess of 128 relative to 127. And subtracting the mass number from the atomic number, right, 127 minus 52, that gives me 75 neutrons, protons. This is the mass number, which is protons plus neutrons. And in the other isotope, it'd be 76. So that'd be an example of the kind of speculation that would get you the point there. And I was pretty lenient on that. Now, speculating about whether it's a metal or a non-metal or a metalloid, or if you're told what group it belonged to, something like that, that's the sort of thing I'm looking for here. Tellurium lies just on the non-metal side of that staircase line, so it might be considered a non-metal or a metalloid. It's also, group 16 has a fairly unknown name. They're the halogens, I guess. I don't know. It's halogens with a C in front of it. Halogens, of course, are group 17. Chalagens, I guess, is the name of that group. Nobody calls it that. In terms of the bonding or ions that form, so tellurium as a non-metal, I'd expect it to participate in covalent bonding. If it formed an ion, it would probably form a -2 ion, because then it would have a xenon electron configuration, so I wouldn't be surprised to see Te2-, which would be called telluride. Then if I look at the periodic trends in terms of atomic radius, we can tell from its position on the periodic table that tellurium is going to be bigger than selenium, and it's going to be bigger than iodine. But it's going to be smaller than antimony and polonium. And if those are the four elements that surround it on the periodic table, that's what I can say about it. In terms of electronegativity, I would guess that it probably has a fairly, average value around 2 or so. I don't think it's going to have a really high electronegativity. It's way over in group 16, but as you go down that group, the electronegativity goes down. By the way, if I was wanting to check some of this stuff out, one place I would look is webelements.com. Of course, you can look many of the stuff up in your textbook. Wikipedia works pretty well for that too. The fancy schmancy periodic table I got on my desk here tells me that the value is 2. It's a periodic table that actually has that value. You may see a slightly different value depending on the units. In terms of ionization energy, tellurium is not going to want to give up an electron. It's going to have a pretty high ionization energy. And the periodic table I have here says 9.01 electron volts. That really doesn't mean anything, but just to give you an example, sodium's is 0.55 electron volts, so it's a high ionization energy. And then in terms of electron affinity, because it's over on the right side of the periodic table, even though it's kind of down the periodic table, it's probably going to want to pick up electrons, and so it's probably going to be, maybe in the more favorable of the middle range of that. But again, I'm just speculating here. My periodic table here says it's 1.97 for electron affinity. I'm going to assume that's probably electron volts as well. Yeah, those are electron volts, which is not normally a unit we deal with. Just by comparison, fluorine is 3.40 in terms of its electron affinity. Hydrogen is 0.75, and sodium would be 0.55 in terms of its electron affinity. Anyway, so that's speculation about those. Didn't see too much of that in that. So that's that first quiz. And again, if you look over in the comments on that quiz, I posted list there and the breakdown of how you did that. Okay, so moving on to the quizzes that were due on September 16th. There's 2 versions of them, so I'll run through them both. What I'm doing here is giving you elements, describing them by generic terms rather than saying a specific element. Obviously, that makes it a little bit harder to look something up online and figure out what the right answer is from resources that aren't really proving that you know what you're doing. If we talk about the elemental ground state of Z here, 1s2, 2s2, 2p, 1s2, that's 2 electrons like that, 2s2, 2 electrons like that, and then in 2p, we've got 5 electrons, so we wind up with 1 that is in the 1 unpaired electron in the ground state, that guy right there. Looking at the next question, same elements, I say that A is going to exist as a diatomic molecule. What's the bond order of A2? So A here, if you look at that, that's going to be 1s2, 2s2, 2p3. These 5 electrons are the valence electrons. So our A electron dot structure is going to look like that. We've got these 5 electrons. We put 1 on each side, and then we double up 1. I did it at the top there. If I have a second A here, it's going to give me the same thing. I'm just going to put the lone pair on the other end. And just doing the sort of Tinker Toy bonding system here, we can see that these 3 electrons, unpaired electrons, all bind up, and we get a nice triple bond there that forms Na2. So triple bond is the correct answer for that one. Now, if we're looking at A and Z, and so if I'm thinking about my periodic table, they are on the first, well, the first row that goes all the way across the second row. And so if we think about that, you know, we've got lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon on that row. 1s2, 2p3 is A, 1s2, 2p5 is Z. So this reveals that Z is actually fluorine and A is actually nitrogen. And the high electronegativity, of course, electronegativity as you go across a period like this is going to increase. And so Z will be our most electronegative of those two. And then I'm asking you to describe the Lewis dot structure. So, you know, we figured out before that A looks like this. Z is going to look like that. So these two, and these two combine, and we wind up with A, Z, Z, Z. The A has a lone pair, the Z's have 3 lone pairs each. So everybody has an octet. We decided that, so we had 5 valence electrons, and here we have 7 valence electrons, and we got 3 of them. So that's 21 valence electrons plus 5, 26 total valence electrons. I have 8 around this Z, 8 around this Z, 8 around that Z. That's 24, and then my 26 is there. If I'm counting octet rules, I just counted them for the Z's. I can also, when counting for A, I count those shared bonds for A as well, so it's got an octet as well. So the question is, how many lone pairs are on the central atom? The answer is 1, which is a way, you know, they'll ask you in a multiple choice question to get a structure correctly. All right, now building off that, we're asked about the electronic geometry. So we have A, Z, And yes, if you got the structure above wrong, you are probably going to miss this question too. That is true. So what we do to figure out the electronic geometry is we classify how many groups of electrons are around the central atom, and there's 1, 2, 3, and 4. The lone pair counts as a group, so there's 4 groups, and of those 4 groups, 1 is a lone pair. Now, the fact that it's 4 groups tells me that it's going to have a tetrahedral electronic geometry. It's going to have sp3 hybridization. The bond angles ideally are going to be around 109.5 degrees, although that may change just a little bit. The fact that it has 1 lone pair and a tetrahedral electronic geometry, that tells us we're going to have a trigonopyramidal molecular geometry. So what the tetrahedron looks like is we have 2 lines that are in the plane, a wedge here showing one coming out, and then a dash thing going back. So we've got A, Z, 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 and then this is the lone pair. So if you look at how the electrons are distributed around A, it's a tetrahedron. If you look at how the atoms are distributed, it looks like a 3-sided pyramid because of the effect of the lone pair on top. So this is asking electronic geometry. The correct answer is tetrahedral. On the next problem, we're asked what's the molecular geometry, and that's trigonopyramidal for the reasons we just said. And we're asked, is this molecule polar or non-polar? So building on the one about electronegativity, okay, to be polar, you have to have both polar bonds, which differ in electronegativity greater than about a 0.3 or 0.4 value, and you've got to have some kind of disturbed symmetry. And, I'll point you back to the determining polarity handout that's right about there at this moment. If you don't have both of these things, then you're nonpolar. So is the A-Z bond polar? Probably so, given that we identified that A is basically nitrogen and Z is basically fluorine. That's going to be polar. Do we have a disturbed symmetry? Absolutely. The lone pair that's on top of this means that the 3 fluorines at the bottom are not symmetrically enough distributed for there to be no net polarity or net dipole. So we would say that the nitrogen has a partially positive charge, the fluorines have a partial negative charge, and that if you look at the center partial negative charge, it's going to be right under the nitrogen, but away from the nitrogen. The dipole vector we draw for that might look like that, sort of. It's going to be a polar molecule. So we were asked true or false. It's nonpolar. False is the answer. It's nonpolar. All right, the second version of the quiz isn't too much different. I just changed the electron configuration, so they're different elements now. This is now equivalent to being carbon. This is now equivalent to being oxygen. So this is, if I look at my electronic configuration, 1s, 2s, 2p, got 2 here, 1, 2, 3, 4. So I have 2 unpaired electrons in the carbon there. This one we're asking now about Z2. So Z is going to have 6 valence electrons. The 2s, 2p4, that's 6 valence electrons. And it's pretty easy to see. Pretty easy to see again that these guys and this guy get together and we form a Z double bond with 2 electrons there. 2 2, 4, 6, 8, 10, 12. That's 12 valence electrons. I had 6 times 2, that's 12, so that checks out. If I count around each C, I've got 2 lone pairs, that's 4, and a double bond, that's 8. So that's a good structure, and double is the answer. Then we're asked about electronegativity. That's going to be Z, obviously, for the same reasons as before. This one is asking about lone pairs around the central atom and the compound. So we're saying it forms a compound with one A. It should have been an ion, 2 minus ion with one A thing. Let me see, pull that back up on another screen. I didn't realize we had that that message in the way there, so we'll make sure I'm getting the question right. Bear with here. So that question. Okay, yeah, that should be a 2 minus ion with 1A and 3Z. Let's see. Bear with me again. So in this one, it said a compound with 1A atom and 3 Z ions. How many lone pairs are on the central atom of the best Lewis dot structure? Okay, so that would be tough. This is, CO3 actually, to my knowledge, doesn't exist. Let's see what it would look like. We've got 6 valence electrons times 3 for the oxygens, and we've got 4 valence electrons times 1 for the carbon. So that's 22 valence electrons. If I take my carbon and put my oxygens around it, I've now used up 6 of those. I've got 16 valence electrons. I now need 6 around each oxygen and 2 around the carbon. So I need 18, so I got to throw a double bond in like that. And so that takes away 2 more electrons. That leaves me with 14. Now I need 6 around each of the other 2 oxygens and 4 around the oxygen with the double bond. That's 14. So no, it's not. That's 16. So I have to draw another double bond, which breaks the rules for carbon. That's the problem with this structure. So that's 12. And so, yeah, this is just not going to work. So that's a mistake on my part. It should have been a 2 minus ion, so I'll give you credit for that. Let's look at the 2 minus ion. So if I have CO3 2 minus, that's again 6 times 3 plus 4 times 1 plus 2 electrons, and the plus 2 electrons comes from the 2 minus ion. So that gives us 24 valence electrons, and that gives us a structure that looks like this. Where essentially the 2 minus charge is carried as a -1 formal charge on each one of those oxygens with a single bond. So that was what I was looking for there, so I'll give this free credit on this one for you. Now the next one does say the ion now, so looking at this ion, we've got 3 regions, or 3 electron groups around carbon. None of those are lone pairs, right? So that means that it's trigonal planar, both in terms of electronic geometry, and then because there's no lone pairs, also the molecular geometry. That's a sp2 hybrid. The bond angle is 120 degrees. So this is going to be trigonal planar electronic, and it's going to be trigonal planar in terms of the molecular geometry of the ion. Then I had to ask you, I didn't want to ask you about CO3 2 minus as to whether it's polar or not, because if you look at the distribution of electrons, you'd say no, it's not. But it's charged, which is kind of like Uber being polar. So I would argue that CO3 2 minus is ionic, which is the extreme end of being polar. So instead, I asked you about Z3. Now, Z3, again, we figured out before that that's really oxygen. Z3 then is going to be the molecule O3, ozone. And if we draw that Lewis dot structure, it winds up looking like this. And this is, we've got just going through it all, it's 3 groups, one of which is a lone pair. So that means it's got a trigonal planar electronic geometry. It has about 120 degree bond angle. It's going to be a little less because of the lone pair. sp2 hybridization again. And molecular geometry is going to be something we call bent or angular. And so the question is it nonpolar? So remember, to be nonpolar, you got to have, to be polar, you've got to have, polar bonds and a disturbed symmetry. And this has got the disturbed symmetry. That lone pair on the central oxygen disturbs the symmetry, but it does not have polar bonds because the electronegativity of oxygen compared to the electronegativity of oxygen, if you subtract those two, it's going to be 0 no matter what it is. So it is true that this is a nonpolar molecule. All right, sorry about the little glitch on the middle thing. I changed that to ion. I didn't get back through. So, but I hope that short little video helps you prepare for tomorrow's exam.